Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected, from the secrets of the cosmos to the marvels of everyday life. Each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you.
Volcanism, the fiery legacy of our dynamic Earth. Volcanism stands as one of nature's most powerful and transformative phenomena, a window into the inner workings of our dynamic planet. This process, which has captivated human curiosity since the dawn of civilization, originates from the immense energies locked within the Earth's interior. The source of this activity is the molten rock known as magma, a substance that forms in the deep mantle as solid rock succumbs to the relentless heat and pressure that prevail beneath the surface. Over time, pockets of magma accumulate, gathering chemical signatures that reflect the varied compositions of the surrounding rocks, and slowly rise through fractures and faults in the Earth's crust. As they migrate upward, these molten materials embody the history of our planet's formation and evolution, carrying within them clues about the processes that have shaped the Earth over billions of years. The generation of magma is a consequence of partial melting, a process that occurs when rock is heated to a point where only some of its components liquefy. This selective melting gives rise to a complex, heterogeneous mixture whose characteristics depend on factors such as temperature, pressure, and the original composition of the rock. Variations in these conditions create distinct types of magma, each with its own viscosity and gas content, which in turn influence the style and intensity of volcanic activity. It is within these subterranean crucibles that the building blocks of volcanic eruptions are formed, setting the stage for a series of events that can profoundly alter the landscape above. Deep within the Earth, the interaction between tectonic forces and thermal energy drives a continuous cycle of rock formation and transformation. The movement of tectonic plates, an ongoing process that reshapes continents and ocean basins, plays a crucial role in this cycle by creating zones of weakness in the crust. These areas become conduits for rising magma, allowing it to breach the surface in the form of volcanic eruptions. Such tectonic settings include convergent boundaries, where the collision of plates forces one beneath another and initiates melting in the subducted material, and divergent boundaries, where plates move apart and facilitate the ascent of magma to fill the void. This intimate connection between tectonics and magma generation underscores the fact that volcanism is not an isolated event but rather a manifestation of the dynamic forces continuously at work beneath the surface of our planet. The behavior of magma as it ascends through the crust is determined by its physical and chemical properties, which dictate whether it will erupt explosively or effuse steadily. In some instances, the magma encounters significant resistance due to the rigidity of overlying rocks, leading to a buildup of pressure that may eventually be released in a violent explosion. In other scenarios, the magma finds a more accommodating path, allowing it to flow more freely and create extended lava fields. These contrasting behaviors are indicative of the diverse outcomes that can arise from the same underlying processes, revealing a complexity that has challenged scientists and inspired countless studies. The interplay between magma viscosity, gas content, and the structural characteristics of the crust above it is a subject of ongoing research, with each discovery shedding new light on the fundamental mechanisms that govern volcanic activity. Understanding the origins and dynamics of volcanism requires a multidisciplinary approach that brings together insights from geology, geophysics, chemistry, and even planetary science. The study of volcanic rocks, or igneous rocks, provides a tangible record of the processes that have taken place deep within the Earth, capturing snapshots of magma as it cools and crystallizes over time. These rocks preserve within their mineral structures the conditions under which they formed, allowing researchers to reconstruct the history of volcanic activity in a given region. In addition, the monitoring of active volcanic sites, using instruments that measure ground deformation, gas emissions, and seismic activity, offers a real-time glimpse into the processes that lead to eruptions. Such observations are crucial for advancing our understanding of how magma moves and evolves beneath the surface, and they help to refine models that predict future volcanic behavior. The study of volcanism not only enriches our knowledge of the Earth's inner workings but also has practical implications for society. The insights gained from investigating the processes that govern volcanic eruptions have a direct impact on hazard assessment and risk management in regions prone to volcanic activity. By deciphering the signals that precede an eruption, scientists aim to improve early warning systems and develop strategies to mitigate the potentially catastrophic effects of volcanic events. The challenge of forecasting eruptions with precision continues to drive innovation in monitoring techniques and analytical methods, underscoring the importance of volcanism as both a scientific puzzle and a societal concern. The majestic and varied forms of volcanoes arise from a complex interplay of eruptive dynamics and the relentless forces of nature that continuously reshape the surface. Over the span of countless years, repeated eruptions add layers of material that gradually mold these natural structures, giving rise to gentle, sprawling shields in some regions and sharply defined, towering peaks in others. The contours of these edifices are a direct consequence of the eruptive style and the evolving interactions between lava flows and the forces of weathering and erosion. Each volcanic episode contributes uniquely to the landscape, leaving behind a geological record that speaks to the power of explosive and effusive events. The material ejected during eruptions, including ash, gas, and particulate matter, often disperses over vast distances and settles to form new layers on the Earth's surface. This deposit of fine sediments can modify the chemical composition of soils and set the stage for dramatic shifts in local ecosystems. When a volcano releases its pent-up energy, the atmospheric repercussions can be profound. The emission of volcanic ash and aerosols into the high layers of the atmosphere can temporarily block sunlight, leading to a reduction in surface temperatures that may persist for months or even years. This climatic influence is not confined to the vicinity of the eruption but can extend globally, altering weather patterns and affecting agricultural productivity in regions far removed from the source. The cooling effect observed following major eruptions serves as a stark reminder of the interconnectedness of Earth's systems, where a single event deep within the crust can trigger changes in the planet's climate. Over time, these climatic shifts are recorded in natural archives such as ice cores and sediment layers, offering scientists valuable insights into the historical interplay between volcanic activity and global climate trends. The imprint of volcanic activity is also deeply woven into the tapestry of human history and culture. Communities living in the proximity of active volcanoes have long witnessed both the creation and destruction wrought by these natural forces. Throughout history, societies have developed intricate methods to predict and respond to eruptions, integrating indigenous wisdom and emerging scientific knowledge to mitigate the risks associated with volcanic hazards. The memories of past eruptions are preserved in local legends and historical records, serving as both cautionary tales and sources of cultural identity. These narratives, passed down through generations, have informed contemporary strategies for disaster management and urban planning in volcanic regions, underscoring the importance of preparing for the unpredictable nature of these events. Moreover, the economic impact of volcanism is profound and multifaceted. The rich, mineral-laden soils resulting from volcanic deposits often provide the foundation for fertile agricultural lands that support vibrant communities. In these regions, the benefits of volcanic activity are tangible, contributing to both local sustenance and broader economic prosperity. However, the very forces that create such abundance also carry inherent risks, as the potential for renewed eruptions looms as a constant reminder of nature's capriciousness. The challenge of balancing economic growth with the need for effective risk management has led to innovative approaches in land use planning and emergency preparedness, as communities strive to harness the positive aspects of volcanic landscapes while safeguarding lives and property. In this phase of exploring the vast realm of volcanism, attention turns to the enduring and far-reaching impacts of volcanic events on the environment and human society. The gradual transformation of landscapes through successive eruptions, the climatic disturbances triggered by airborne ash and gases, and the cultural narratives woven around these phenomena all contribute to a richer understanding of the dynamic processes at work. Each eruption, regardless of its scale, leaves an indelible mark on the Earth, influencing natural cycles and human endeavors alike. The legacy of volcanism is thus not confined to the immediate aftermath of an eruption but extends across time, shaping ecosystems, climate, and the very fabric of civilization. This intricate web of interactions invites us to appreciate the delicate balance between creation and destruction, and to recognize that the story of our planet is one of continual evolution driven by the powerful forces hidden beneath the surface. Recent advances in remote sensing and satellite imaging have revolutionized the way scientists monitor volcanic systems, enabling continuous observation of remote and hazardous regions with unprecedented clarity and precision. This technological progress, complemented by ground-based instruments and drone surveillance, has opened up opportunities to capture subtle changes in the volcanic edifice and its surroundings that were once imperceptible. The integration of these diverse data streams into sophisticated computational models allows researchers to simulate complex volcanic processes with increasing accuracy, paving the way for improved forecasting of eruptive events and a deeper understanding of the underlying mechanisms. In parallel with these observational advancements, the field of volcanology is undergoing a paradigm shift driven by the rapid evolution of data analytics and machine learning. By harnessing the power of artificial intelligence, scientists are now able to sift through vast quantities of geophysical data to identify patterns and precursors to volcanic activity that might otherwise remain hidden. These innovative approaches not only enhance the predictive capabilities of hazard assessments but also contribute to the formulation of new theories that challenge traditional models of volcanic behavior. The synergy between computational power and geoscientific insight is proving to be a fertile ground for discovery, offering fresh perspectives on long-standing questions about the evolution and dynamics of volcanic systems. Beyond the technical realm, the study of volcanism is increasingly intersecting with planetary science, broadening its scope to encompass the volcanically active landscapes of other celestial bodies. The volcanic features observed on planets and moons within our solar system, from the restless plumes on Jupiter's moon Io to the ancient lava flows on Mars, provide critical comparative insights that enrich our understanding of planetary formation and evolution. These extraterrestrial analogues serve as natural laboratories, where the interplay of heat, pressure, and chemical processes can be studied in environments that differ markedly from Earth. Such comparative studies not only illuminate the universal principles governing volcanic activity but also inform theories about the conditions necessary for sustaining life and the geological evolution of rocky worlds. As the boundaries of volcanology expand, the importance of international collaboration and data sharing becomes ever more apparent. Global networks of observatories, research institutions, and governmental agencies are forging partnerships that transcend geographical and disciplinary borders, fostering an environment of shared knowledge and collective problem-solving. This cooperative spirit is essential for addressing the multifaceted challenges posed by volcanic hazards, from the need to develop robust early warning systems to the formulation of effective risk mitigation strategies. The combined efforts of a global scientific community ensure that insights gained from one volcanic event can be rapidly disseminated and applied to others, thereby enhancing resilience in regions prone to volcanic activity. In this evolving landscape, the promise of future discoveries remains as vibrant as ever. The convergence of advanced monitoring technologies, innovative computational techniques, and a broadened perspective that encompasses planetary science heralds a new era in the study of volcanism. As researchers continue to peel back the layers of complexity inherent in volcanic systems, they are not only unraveling the mysteries of these extraordinary natural events but also contributing to a deeper, more integrated understanding of the dynamic processes that shape our universe. The ongoing journey into the heart of volcanism stands as a testament to human ingenuity and curiosity, illuminating the path toward a future where the power of nature is harnessed for knowledge, preparedness, and the continued exploration of our planetary heritage.